What if I told you the most violent explosions in the universe are so powerful, they can be seen from billions of light years away, blazing across the cosmos like intergalactic fireworks? These aren't just any cosmic events, they're gamma-ray bursts, the single most energetic phenomena since the Big Bang itself. For a fleeting moment, these bursts outshine entire galaxies, releasing more energy in seconds than our Sun will in its entire lifetime. And today, we're embarking on a journey to uncover 30 mind-blowing facts about the most distant gamma-ray bursts ever detected. Cosmic beacons so far away, their light has traveled across space and time just to reach us. Picture this: you're a cosmic detective, piecing together clues from the edge of the observable universe. These distant gamma-ray bursts are like messages in a bottle, sent from the earliest chapters of cosmic history. They're not just flashes in the dark, they're windows into the extreme physics of collapsing stars, the birth cries of black holes, and maybe even the secrets of the universe's expansion. Some of these bursts erupted when the universe was just a fraction of its current age, and their light has been racing toward us ever since, carrying stories of chaos and creation written in gamma rays. But here's what's truly thrilling: every burst we detect is a puzzle waiting to be solved. How do they form? Why are some brighter than others? And what can they teach us about the farthest reaches of space and time? Buckle up, because we're about to dive into a world of hyper-distant explosions, bizarre physics, and the kind of cosmic drama that reshapes our understanding of reality. By the time we're done, you'll see the night sky and the universe itself in a whole new light. So let's begin this adventure, one astonishing fact at a time. The sheer scale of a gamma-ray burst is almost impossible to grasp until you realize a single one can outshine every star in its galaxy combined. Imagine a cosmic flamethrower so intense, its glare briefly drowns out the collective light of hundreds of billions of stars. That's not science fiction, it's exactly what happens when a distant GRB erupts. These explosions don't just flicker in the darkness, they dominate it, turning their host galaxies into faint backdrops for a split-second spectacle of unimaginable power. Take GRB 080319b, for example. This monster detonated 7.5 billion light-years away. So distant, its light had traveled more than half the age of the universe before reaching us. Yet for 30 seconds, it burned so fiercely that under perfect conditions, you could have spotted it with your naked eye. Just think about that, a flash from a time before Earth even existed, visible without a telescope, as if someone had lit a match in another galaxy, and for a moment, it outshone every star in our sky. The physics behind this is even wilder. A typical GRB channels more energy in seconds than our Sun will emit across its entire 10 billion-year lifespan. It's like comparing a nuclear bomb to a birthday candle, and while galaxies glow steadily from countless stars, a GRB focuses all that violence into a narrow beam, cosmic lightning screaming across the void. Scientists call this relativistic beaming, where particles surge at nearly light speed, concentrating the explosion's fury into twin jets that slice through space like celestial lasers. Miss the beam and you'd never know it happened, but if Earth catches even a glancing blow, telescopes light up like a cosmic alarm bell. What makes these bursts truly humbling is their role as universal yardsticks. Because they're so dazzling, we can spot them across staggering distances like lighthouses in the fog of the early universe. Each one is a time capsule, carrying data from epochs when galaxies were just assembling, and the cosmos was a chaotic nursery of raw energy. And the farther we look, the more they reveal about how space itself has stretched and twisted over billions of years. So next time you glance at the night sky, remember, somewhere out there, a GRB might be erupting right now, turning a distant galaxy's quiet glow into the universe's most brilliant blink, and you'll miss its spectacle. Scientists have witnessed countless gamma-ray bursts over the decades, but nothing could prepare them for the monster that ripped through the cosmos in October 2022. Known as GRB 221009A, this wasn't just another cosmic explosion, it was the brightest gamma-ray burst ever recorded, earning it the nickname the BOT, brightest of all time. Detected from 2.4 billion light-years away, this explosion was so violent, it didn't just light up telescopes, it literally shook Earth's upper atmosphere. For 300 seconds, this single burst unleashed energy equivalent to a supernova, except instead of unfolding over weeks, it compressed all that fury into mere minutes. Imagine taking the death throes of a massive star, squeezing them into the runtime of a pop song, and then dialing the brilliance up to 11. The numbers are staggering. The BOT's energy output surpassed 1,000,000 trillion times the luminosity of our Sun. To put that into perspective, if you could harness just 1 second of its power, it would outstrip all human energy consumption since the dawn of civilization. But here's where it gets even wilder. Normally, gamma-ray bursts fade into obscurity after their initial flash. This one, it left a lingering afterglow so intense, it disrupted Earth's ionosphere, the electrically charged layer of our atmosphere that bounces radio signals around the planet. Satellites detected disturbances usually linked to solar storms, except this wasn't the Sun's doing. A blast from halfway across the universe had briefly rewritten the rules of our planet's atmospheric physics. Astronomers suspect the BOT was a long-duration burst, likely triggered by the collapse of a hypermassive star into a newborn black hole. As the star's core imploded, twin jets of plasma shot outward at near light speed, punching through the stellar corpse like a cosmic blowtorch. What we witnessed was the jet pointed almost directly at Earth, a bullseye of annihilation so precise, it's like winning the universe's deadliest lottery. What makes this burst truly historic isn't just its record-breaking brightness, but its timing. The BOT erupted at a golden age for gamma-ray astronomy. With advanced instruments like NASA's Swift and Fermi telescopes, plus a global network of ground-based observatories, scientists captured this event with unprecedented detail. It's as if the universe handed us a firing squad of data, letting us study the inner workings of these cataclysms like never before. And the best part, we're still unraveling its secrets. The BOT's light carried clues about magnetic fields in the early universe, the formation of heavy elements, and even the nature of space-time itself. Every photon was a breadcrumb leading us deeper into the cosmic labyrinth. So while the flash is long gone, its legacy burns brighter than ever in the annals of astronomy, proof that sometimes the universe doesn't just whisper its secrets. It screams. Gamma-ray bursts don't just light up the cosmos, they're time machines. Every distant flash we detect is a snapshot of the universe's past, frozen in light that's traveled across eons to reach us. Take GRB 090423 for instance. When astronomers caught its glow in 2009, they weren't just seeing an explosion, they were staring 13 billion years into the past. This burst erupted when the universe was a mere 630 million years old, a cosmic toddler still taking its first shaky steps. Think of it like unearthing a fossil, but instead of bones, we've found the remnants of a cataclysm from the universe's childhood. The light from GRB 090423 began its journey before Earth existed, before the Milky Way took shape, even before most stars had ignited. By the time it reached us, the universe had expanded so dramatically that the burst's light stretched into infrared wavelengths, a relic of an era when space itself was smaller, denser, and far more chaotic. What makes these ancient bursts so valuable isn't just their age, it's what they reveal about the early cosmos. Back then, the universe was a murky place, filled with primordial hydrogen gas that hadn't yet been cooked into heavier elements. GRB 090423's afterglow gave scientists their first peek into this cosmic dawn, showing them the conditions that existed before galaxies as we know them had fully formed. It's like finding a letter from the universe's infancy, scribbled in gamma rays and sealed with the fingerprints of physics we're still trying to decode. But here's the kicker: detecting these bursts is like trying to spot a firefly in a foggy forest. The farther back we look, the fewer GRBs we find, not because they weren't happening, but because the early universe was so thick with gas that many bursts light was absorbed before it could escape. That makes every ultra-distant GRB we catch a statistical miracle, a 1 in a billion cosmic flare that fought its way through the fog of time to tell us its story. And stories they do tell. The afterglows of these ancient bursts act as backlights, illuminating the gas clouds they pass through. By analyzing how their light gets absorbed, astronomers can map the distribution of matter in the early universe, measure its temperature, even track how the first heavy elements spread through space. It's like using a gamma-ray flashlight to study the shadows of a room that vanished billions of years ago. So when you hear about a distant gamma-ray burst, remember, you're not just witnessing an explosion. You're seeing a message in a bottle tossed into the cosmic ocean when the universe was young, finally washing ashore in our telescopes. And with every new burst we catch, we're piecing together a scrapbook of the cosmos's earliest, most violent moments, one flash at a time. Not all gamma-ray bursts announce themselves with a fireworks show. Some of the universe's most violent explosions play hide and seek, unleashing torrents of gamma rays while leaving almost no visible trace. Astronomers call these enigmas dark bursts, and they're among the most puzzling phenomena in high-energy astrophysics. Picture a cosmic bomb detonating in the shadows, its gamma-ray scream piercing the darkness, but its light snuffed out before we can fully glimpse the source. Take GRB 070306, a burst that defied expectations. When satellites first detected its gamma-ray flare, telescopes worldwide swung into action, expecting the usual brilliant afterglow. Instead, they found nothing. For 48 hours, astronomers scoured the skies, chasing a ghost. Just as they were about to give up, a faint infrared glow finally emerged, like a dimmer switch slowly turning up in a pitch-black room. This wasn't just a delayed reaction, it was evidence of something blocking our view, a celestial curtain drawn across the explosion's aftermath. So what's obscuring these bursts? One leading theory points to colossal dust clouds, the cosmic equivalent of smoke shielding a wildfire. When a GRB erupts inside a galaxy choked with stellar debris, those dust particles can absorb visible light while allowing gamma rays to pass through. It's like watching a flashlight beam through fog. The high-energy photons punch straight through, but the visible light gets scattered and absorbed. Another possibility involves geometry. If we're viewing the burst from an off angle, the visible afterglow might be beamed away from us while gamma rays spray in all directions. Imagine a lighthouse where the rotating beam misses your ship. You'd only see the faint glow of its windows, not the piercing spotlight. Dark bursts force us to rethink how we study these cosmic explosions. Normally, astronomers rely on afterglows to pinpoint GRB locations and study their host galaxies. But when the light vanishes, it's like investigating a crime scene where the perpetrator erased their fingerprints. That's why events like GRB 070306 are so valuable. They're teaching us to read the universe in infrared and radio wavelengths, peeling back the dust layers to reveal the hidden hearts of these explosions. What's fascinating is that dark bursts might not be rare. We could be missing them by the dozens. Current estimates suggest up to 1/3 of all GRBs could fall into this category, their visible light smothered before it reaches us. That means every time we detect a gamma-ray flash with no afterglow, we might be standing at the edge of a discovery, staring into one of the universe's best-kept secrets. And as telescopes grow more sensitive to infrared and other non-visible light, we're finally lifting the veil on these shadowy giants, proving that sometimes the cosmos saves its most spectacular shows for those who know how to look in the dark. Deep in the cosmic archives, there's a flash of light so ancient it borders on the edge of time itself. Meet GRB 090429b, a gamma-ray burst that holds the record for distance, a staggering 13.14 billion light-years away. That means this explosion erupted when the universe was just 520 million years old, a mere infant by cosmic standards. To put that into perspective, this burst detonated so early in cosmic history that the first galaxies were barely flickering to life, and the universe was still emerging from its dark ages, a foggy era before stars had fully illuminated the void. What makes this burst extraordinary isn't just its age, it's the language it speaks. Astronomers measured distance in the early universe using something called redshift, denoted by the letter Z. The higher the redshift, the farther and older the object. GRB 090429b clocks in at a redshift of around 9.4, a number so extreme it places this burst among the top contenders for the title of most distant object ever observed. At these distances, the universe's expansion has stretched the burst's light into the infrared, a faint whisper of its original fury, like a scream slowed to a murmur over billions of years. But confirming a distance this extreme isn't as simple as snapping a photo. When dealing with objects from the universe's infancy, ambiguity lurks at every turn. GRB 090429b's light was so faint and redshifted that astronomers had to rely on indirect methods to estimate its distance, analyzing the way its afterglow interacted with intervening gas clouds. It's like trying to identify a song played through a wall. You hear the muffled notes, but piecing together the original melody takes painstaking detective work. The challenges don't end there. At these distances, even the most powerful telescopes struggle to distinguish between a true primordial burst and a closer imposter. Dust, cosmic expansion, and the faintness of the signal all conspire to muddy the waters. Some scientists initially questioned whether GRB 090429b's redshift was as high as claimed, suggesting alternative explanations for its unusual spectral features. It wasn't until multiple teams cross-checked their data, combining observations from Hubble, Keck, and other observatories, that the case for its record-breaking distance grew stronger. Yet despite the hurdles, GRB 090429b offers a treasure trove of insights. Its existence tells us that massive stars and the black holes they birth were already forming when the universe was less than 4% of its current age. That's like finding a skyscraper in the ruins of an ancient civilization thought to have only built huts. It challenges our models of how quickly the first stars ignited and how rapidly the cosmos evolved from primordial simplicity to the structured universe we see today. And here's the haunting part. We're only seeing this burst now because its light has taken 13 billion years to reach us. By the time its glow finally hit our telescopes, the star that created it, and likely the entire galaxy it called home, had long since vanished, consumed by the relentless expansion of space. We're not just observing a burst, we're catching the last echo of a universe that no longer exists, a fossilized scream from the cosmic dawn. So why keep searching for these record breakers? Because each one is a benchmark, a signpost in the uncharted wilderness of the early universe. With every distant GRB we confirm, we redraw the map of cosmic history, pushing our understanding closer to the moment when the first stars flickered on and the darkness began to lift. And somewhere out there, even farther bursts may still be racing toward us, their light carrying secrets from a time before time, if only we're patient enough to wait. Imagine the universe's most spectacular jewelry workshop, a place where gold, platinum, and other precious metals aren't mined, but forged in the heart of collapsing stars. Gamma-ray bursts might seem like pure destruction, but hidden in their fiery aftermath lies one of nature's most astonishing secrets. They're cosmic factories for the heaviest elements in the periodic table. When certain distant GRBs erupt, they don't just leave behind devastation, they scatter newly minted gold across interstellar space in a process so elegant, scientists call it interstellar alchemy. This isn't science fiction. Back in 2017, astronomers witnessed a groundbreaking event, a short gamma-ray burst paired with something called a kilonova. This wasn't just any explosion, it was the violent merger of two neutron stars, ultra-dense stellar corpses spinning toward each other in a deadly dance. As they collided, the resulting GRB spewed out jets of energy, while the merger itself ejected a cloud of neutron-rich material at blinding speeds. Inside that swirling maelstrom, atomic nuclei captured free neutrons faster than they could decay, building heavier and heavier elements in a process known as rapid neutron capture, or the R process. Within seconds, this cosmic pressure cooker created elements like gold, platinum, and uranium, the very metals we prize in jewelry and technology. Calculations suggest a single neutron star merger can produce hundreds of Earth masses worth of gold, flung into space like glitter from a shattered cosmic piñata. That means the ring on your finger might contain atoms forged in a GRB's kilonova billions of years ago, stardust recycled through supernova and planetary formation until it found its way to Earth. What's mind-blowing is how efficiently these events cook up rare elements. While ordinary stars fuse lighter atoms like hydrogen and helium, they can't muster the extreme conditions needed to forge gold. That requires something far more violent, a neutron star collision's absurd temperatures, densities, and neutron floods. Picture two city-sized objects, each more massive than our Sun, smashing together so hard they briefly create a black hole while simultaneously spraying the universe with enough gold to gild entire planets. The implications are staggering. If short GRBs with kilonovae are indeed the universe's primary gold factories, then every precious metal on Earth, from the tungsten in your phone to the platinum in catalytic converters, owes its existence to these cataclysmic mergers. It means that without GRBs, our planet might never have formed with the heavy elements necessary for life as we know it, yet mysteries remain. How often do these productive collisions happen? Are some GRBs better at manufacturing heavy elements than others? And how far back in cosmic history did this alchemy begin? Each new kilonova detection brings us closer to answers, turning what was once theoretical into observable fact. So the next time you admire a piece of gold jewelry, remember, it's not just an accessory. It's a relic of one of the universe's most violent and beautiful transformations, a whisper from the kilonova forges that shaped everything from smartphone circuits to the rings of Saturn. Gamma-ray bursts don't just blast light across the cosmos, they might be firing ghostly bullets of pure energy too. Meet the neutrino, one of the universe's most elusive particles, a cosmic phantom so intangible it can pass through entire planets without leaving a trace. These aren't just any subatomic particles, they're ultra-high energy messengers, potentially forged in the same cataclysmic fires that power GRBs. And if scientists are right, catching one of these neutrinos could crack open the hidden physics behind the universe's most violent explosions. Take the case of GRB 190114C, a burst detected in January 2019, 4.5 billion light-years away. This eruption was already fascinating, but it got even stranger when the Ice Cube Observatory, a neutrino detector buried deep in Antarctic ice, recorded a high-energy neutrino arriving from roughly the same direction at nearly the same time. The odds of this being a coincidence about 1 in 500. It was like finding a fingerprint at a crime scene, except the suspect was a particle moving at near light speed from another galaxy. Why does this matter? Neutrinos rarely interact with matter. Trillions pass through your body every second without a single collision. But the ones linked to GRBs aren't your average neutrinos. They're cosmic speed demons, accelerated to energies millions of times greater than anything our particle colliders can produce. If GRBs truly generate these particles, they'd act as microscopic probes, carrying undisturbed information about the explosion's inner workings, details light alone can't reveal. Imagine trying to study a nuclear blast by analyzing the shrapnel. Neutrinos are that shrapnel, offering clues about the detonation's heart. The hunt for these ghostly signals is anything but easy. Ice cube sensors span a cubic kilometer of pristine ice, waiting for the rare moment a neutrino crashes into an atom, creating a faint blue flash called Cherenkov radiation. Even then, pinpointing a neutrino's origin is like tracing a raindrop back to a single cloud in a thunderstorm. That's what made the GRB 190114C connection so tantalizing. It was the first time a high-energy neutrino seemed to whisper, "I came from there." But here's the twist. Not all theorists are convinced. Some argue the neutrino-GRB link could still be a statistical fluke, or that other cosmic accelerators, like supermassive black holes, might be the real neutrino factories. After all, the universe is a noisy place and ghost particles don't leave return addresses. Yet with every new GRB detected, IceCube's team scours their data, hoping for another cosmic coincidence that might solidify the connection. What's at stake goes beyond neutrinos. If GRBs are slinging these particles across the universe, they're likely doing so via mechanisms we've barely begun to understand. Perhaps through shock waves in magnetized plasma or the turbulent environments around newborn black holes. Each neutrino we catch is a puzzle piece, helping us map the invisible scaffolding of particle physics in environments more extreme than any lab. So while the evidence isn't yet bulletproof, the chase is rewriting the rules of multi-messenger astronomy. The idea that to truly understand cosmic events, we need to study not just light but particles, gravitational waves, and anything else the universe throws our way. GRBs might be the ultimate particle accelerators and neutrinos their faint, fast-traveling shadows. And if we're lucky, the next big burst might send another ghost our way, offering a fleeting glimpse into the heart of the universe's most dazzling explosions. Gamma-ray bursts do more than dazzle us with their brilliance. They bend the very fabric of reality, giving scientists a cosmic laboratory to test Einstein's theory of relativity in ways no earthbound experiment ever could. One of the most mind-bending discoveries came from GRB 090510, a burst that erupted 7.3 billion light-years away. When NASA Fermi Telescope caught its gamma rays in 2009, something peculiar stood out. High-energy photons arrived at Earth a fraction of a second later than their lower-energy counterparts. On the surface, that delay might seem trivial, but in the world of physics, it was like finding a crack in the universe's rulebook. Einstein's relativity insists that all light, regardless of energy, should travel at the same speed in a vacuum, a constant that underpins everything from GPS satellites to our understanding of cosmic distances. Yet if certain quantum gravity theories are correct, space-time at microscopic scales might behave more like froth, with tiny bubbles that could subtly slow down higher energy photons. It's as if the universe has hidden speed bumps, invisible to us but detectable when gamma rays race across billions of light-years. GRB 090510's split-second delay offered the first tantalizing hint that Einstein's perfect, smooth space-time might have imperfections when examined at energies approaching the quantum realm. The stakes couldn't be higher. Confirming these delays would mean glimpsing the unified theory of quantum gravity physics' holy grail, a framework that reconciles Einstein's cosmos with the chaotic quantum world. Think of it like watching waves in the ocean. Relativity describes the vast, rolling swells, while quantum mechanics deals with the spray and foam of individual droplets. Gamma-ray bursts let us study where those two realms might collide. What makes GRBs ideal for this test is their sheer distance. The farther light travels, the more any subtle speed difference adds up, like a sprinter slowly falling behind over a marathon rather than a dash. GRB's 0905-107 billion-year journey amplified that effect, turning a theoretical whisper into something Fermi's detectors could potentially hear. And while the delay Fermi observed was achingly small, just 0.9 seconds between the highest and lowest energy photons, it was enough to rule out some quantum gravity models while keeping others in play. But here's the twist: not all bursts show this behavior. Some GRBs have photons that arrive in perfect sync, complicating the picture. Could it be that space-time's texture varies across the universe, like patches of rough and smooth sea? Or are other factors like magnetic fields in intergalactic space muddying the data? The answer might lie in catching even more distant bursts, where the cumulative effect of any quantum froth would be impossible to ignore. That's why telescopes keep scanning the skies, waiting for the next GRB that could tip the scales. Every burst is a roll of the cosmic dice, a chance to probe the universe's deepest laws under conditions no lab could ever replicate. And if one day we confirm that gamma rays don't all travel at the same speed, it won't just rewrite textbooks, it'll reveal a universe far stranger, far more intricate than even Einstein dared dream. Until then, each flash from the distant cosmos keeps us guessing, teasing secrets from the quantum shadows. Sometimes the universe plays tricks on us, sending cosmic signals that defy every rule in the book. Take GRB 060218, a burst that didn't just break the mold. It left astronomers scratching their heads when its afterglow appeared without the gamma-ray fanfare that usually announces these explosions. Picture waiting for a thunderclap but only hearing the distant rumble, no lightning in sight. That's the essence of an orphan afterglow, a ghostly echo of a gamma-ray burst that somehow slipped past our detectors, leaving behind only its fading afterparty. This particular burst erupted 440 million light-years away, relatively close by cosmic standards, yet its gamma rays were so faint they nearly missed detection. What made it unforgettable was the afterglow, bright, lingering, and utterly mismatched with the weak initial burst. It's like finding a smoldering campfire but no evidence of the match that started it. Scientists dubbed these events cosmic shy guys, as if the universe was hiding its most explosive acts behind a curtain, only letting us see the aftermath. So how does an afterglow outshine its own explosion? One leading theory points to off-axis jets, the cosmic equivalent of a flashlight aimed just slightly away from your eyes. Gamma-ray bursts channel their energy into narrow beams, and if Earth isn't perfectly aligned with that beam, we might only catch a sidelong glimpse of the gamma rays while the broader afterglow, radiating in all directions, lights up our telescopes. Imagine a lighthouse where the rotating beam never directly faces you. You'd see the glow of its windows but miss the piercing spotlight. Another possibility involves bursts that stretch the definition of short. Most GRBs last anywhere from milliseconds to minutes, but some might flicker unusually slowly, emitting gamma rays so spread out they fall below our detection thresholds. It's like trying to spot a strobe light set to the slowest pulse. You might miss the flashes entirely, only noticing the ambient glow they leave behind. For GRB 060218, this could mean the burst was a marathoner in a sprinting race, its energy dispersed over hours rather than seconds. The intrigue deepens when you consider what these orphans reveal about the universe's hidden explosions. If off-axis jets are common, we might be missing a significant fraction of gamma-ray bursts simply because we're not in the line of fire. That raises a tantalizing question. How many cosmic fireworks have we overlooked, their afterglows fading unnoticed because the main event was pointed elsewhere? Some estimates suggest orphan afterglows could outnumber traditional GRBs, hinting at a shadow population of bursts lurking just beyond our observational limits. What's remarkable is how these shy guys challenge our tools and assumptions. Modern satellites like Swift and Fermi are tuned to catch the initial gamma-ray flash, the universe's version of a starter pistol. But orphans remind us that sometimes the real story unfolds in the quiet aftermath, in wavelengths our eyes can't see and our detectors might overlook. They're cosmic breadcrumbs leading us to rethink where and how we search for the universe's most violent explosions and perhaps the most humbling thought. Every orphan afterglow could be a missed opportunity, a burst whose secrets will never fully unravel because its brightest moment passed unseen. Yet with each one we catch, we refine our hunt, learning to listen for the universe's whispers as keenly as it screams. So while GRB 060218 might have played hard to get, it taught us something invaluable. Sometimes the cosmos saves its best performances for those willing to read between the lines. Gamma-ray bursts aren't just cosmic explosions, they're celestial census takers, quietly recording where and when stars were born across the universe's history. The key lies in their intimate connection to massive stars. Since most long GRBs mark the deaths of short-lived hypergiant stars, their frequency directly mirrors how many such stars were forming at any given cosmic epoch. It's like finding a graveyard where the tombstones tell you not just when lives ended, but how many lives began during a specific era. This revelation came into sharp focus in 2013, when astronomers analyzing hundreds of GRBs made a startling discovery. These bursts were 10 times more common 11 billion years ago compared to today. That period, nicknamed Cosmic Noon, was the universe's wild teenage years, a time when galaxies were churning out stars at a ferocious rate, turning pristine gas into stellar furnaces at a pace the modern cosmos can't match. Every distant GRB from this era is essentially a flare gun shot into the void, signaling another stellar nursery operating at maximum capacity. The data paints a vivid picture. Imagine rewinding the universe to cosmic noon. Galaxies would appear bluer and more chaotic, their spiral arms thick with newborn stars. Supernova would light up every few weeks in a typical galaxy instead of every century. And amidst this stellar frenzy, gamma-ray bursts, the rarest, most extreme stellar deaths, would erupt about once per 100,000 years per galaxy instead of the current once per million-year tempo. That's the difference between a quiet suburban neighborhood and a metropolis in the middle of rush hour. What makes GRBs such powerful star formation probes is their visibility across unimaginable distances. While ordinary starlight from early galaxies often gets drowned out by cosmic expansion, GRBs punch through the noise like a foghorn in the dark. Their brilliant flashes allow astronomers to sample star formation in galaxies too faint or distant to study directly, filling in gaps where traditional telescope surveys fall short. It's akin to using lightning strikes to map a thunderstorm's extent when the rain clouds themselves are invisible. But the story isn't just about counting bursts. Subtle patterns in their distribution reveal how star formation varied across different cosmic environments. Some studies suggest GRBs were slightly more frequent in smaller, metal-poor galaxies, hints that the first generations of stars, born from pure hydrogen and helium, might have been especially prone to producing these explosive deaths. Others show bursts clustering along the web-like filaments of matter where galaxies formed, tracing the universe's large-scale skeleton in gamma rays instead of starlight. Perhaps most remarkably, this GRB star formation census aligns with independent measurements from galaxy surveys, creating a consistent timeline of cosmic history. When astronomers compare GRB rates to other star formation indicators, like ultraviolet light from young stars or emissions from interstellar dust, the pieces fit together like a jigsaw puzzle viewed through different colored lenses. That convergence gives scientists confidence they're not just seeing random flashes, but decoding a fundamental rhythm of the cosmos, the rise and fall of stellar births across 13 billion years. So the next time you hear about a distant gamma-ray burst, remember, you're not just witnessing a stellar catastrophe. You're seeing a time-stamped report from the universe's most prolific star factories, a beacon that illuminates how galaxies grew from primordial specks into the glittering spirals we know today. And with every new burst detected, we refine our understanding of cosmic noon, that brief, brilliant epoch when the universe burned brightest with the fires of creation. For 50 years, gamma-ray bursts were the universe's greatest enigma, flashes of invisible light haunting military satellites, dismissed as secret nuclear tests before astronomers even knew they existed. The mystery began in the 1960s when America's Vela satellites, designed to monitor Soviet atomic detonations, started picking up eerie gamma-ray spikes with no earthly origin. Classified documents from that era reveal the confusion. Pentagon scientists dubbed them gamma-ray anomalies, scribbling in margins that the signals seemed to come from deep space. But with Cold War tensions running high, the data stayed locked away, leaving astronomers in the dark about these cosmic intruders. It wasn't until May 8, 1997 that the veil finally lifted. GRB 970508, a burst erupting 6 billion light-years away, became the Rosetta Stone of high-energy astronomy. For the first time, rapid follow-up observations caught its fading afterglow in visible light, allowing astronomers to triangulate its home galaxy. That breakthrough transformed GRBs from military curiosities into cosmic landmarks, proving they weren't neighborhood events in our solar system or even our galaxy, but explosions echoing across the observable universe. The contrast between then and now couldn't be starker. Early Vela satellites had crude directional accuracy. Some bursts were localized only to within a quarter of the sky, leaving astronomers chasing ghosts with little more than hunches. Today's observatories like Swift and Fermi pinpoint GRBs within seconds, triggering global networks of telescopes that dissect every wavelength from radio to gamma rays. Where once we saw only brief flickers, we now trace entire life cycles. The initial blast, the afterglow's slow fade, even the birthplaces of these explosions in distant galaxies. Declassified Vela records from 1973 show just how far we've come. One memo describes bursts as isotropic but non-uniform, a bureaucratic way of saying they appeared everywhere but clustered nowhere, a clue that GRBs were either incredibly close or impossibly distant. It took another 24 years and GRB 970508's afterglow to settle the debate. That burst's redshift measurement proof of its epic distance was the final nail in the coffin for local theories, revealing these flashes as the universe's most powerful explosions since its birth. What's astonishing is how much hung on that one detection. Before 1997, astronomers debated whether GRBs came from comets colliding in our solar system or neutron stars in the Milky Way's halo. Afterward, the playing field expanded to the entire cosmos. The Vela satellite's accidental discovery had set the stage, but GRB 970508 rewrote the script, proving these bursts were the death cries of stars in galaxies so distant. Their light had traveled most of the universe's age to reach us. Modern multi-messenger astronomy has turned this revelation into a precision science. When a GRB flares today, it's not just telescopes that spring to action. Gravitational wave detectors, neutrino observatories, and even atmospheric monitors join the hunt, each instrument adding another layer to the story. We've gone from squinting at single-frame snapshots to directing a cosmic blockbuster, with GRBs as the starring actors. And it all traces back to that pivotal moment in 1997, when a flicker of visible light 6 billion years in the making finally told us where to look. Some gamma-ray bursts might owe their terrifying power to cosmic monsters with magnetic fields so strong they could erase your credit card from halfway across the galaxy. Meet magnetars, the universe's ultimate magnetic powerhouses. Born from the collapse of massive stars, these neutron stars pack the sun's mass into a city-sized sphere, spinning faster than a kitchen blender while wielding magnetic fields 1,000 trillion times stronger than Earth. And when one of these hypercharged zombies gets involved in a gamma-ray burst, the results rewrite the rules of physics. Take GRB 1914c, the brightest of all time burst we mentioned earlier. While most GRBs tap into the raw energy of collapsing stars or colliding neutron stars, this one had an extra twist. Photons with energies exceeding 100 tera-electronvolts, that's billions of times more energetic than visible light. For years, theorists suspected such extreme emissions might require something beyond a standard black hole birth. Enter the magnetar model, where the star's corpse doesn't just collapse quietly. It leaves behind a spinning, magnetized dynamo capable of turbocharging the explosion. Here's how it works. As a massive star collapses, its core might form a magnetar instead of instantly becoming a black hole. For precious seconds or minutes, this newborn magnetar's ludicrous magnetic field acts like a cosmic particle accelerator, channeling the explosion's energy into focused jets. Picture a fire hose with the pressure cranked to infinity, except instead of water, it's blasting electrons and protons to near light speed, forcing them to emit those record-breaking tera-electronvolt photons in the process. The magnetic field becomes a lens, bending the burst's fury into beams so intense they'd pierce through entire galaxies. What makes magnetar-powered GRBs special isn't just their brightness, it's their fingerprints. The 100 tera-electronvolt photons from GRB 1914C were smoking gun evidence of particles being accelerated beyond anything seen in typical bursts. Regular neutron stars can't muster that kind of energy. Their magnetic fields are strong but nowhere near magnetar levels. It's like comparing a refrigerator magnet to the electromagnet used to lift cars in a scrapyard. Only a magnetar's ridiculous physics could slam particles hard enough to spit out gamma rays that outshine the Large Hadron Collider's most violent collisions. But there's a catch. Magnetar involvement might solve one mystery while creating others. These stars are rare, only about 30 confirmed exist in our galaxy, so if they're behind some distant GRBs, it suggests the universe's early epochs bred them more prolifically. Perhaps lower metal content in early stars made magnetar formation more likely, or maybe their extreme environments left unique chemical traces in ancient galaxies. Every magnetar-linked GRB becomes a time capsule, preserving clues about how stellar evolution worked when the cosmos was young. The implications stretch even further. Some theorists speculate that magnetar-powered GRBs could be the cosmic factories for ultra-high-energy cosmic rays, those mysterious particles that strike Earth's atmosphere with the force of a fast-pitch baseball. If true, then every time we catch a burst like GRB 1914C, we're glimpsing the engines that seed the universe with particles no human accelerator could ever hope to produce. Yet for all their might, magnetars are fleeting players. Most succumb to their own intensity within millennia, their magnetic fields gradually decaying until the star goes dark. That makes every GRB they power a last, defiant blaze of glory, a magnetic monster's final roar before silence. And when we detect these bursts from billions of light years away, we're effectively watching their obituaries written in gamma rays and delivered across eons. So next time a record-breaking GRB flares in the darkness, listen closely. It might just be the universe's most powerful magnet, screaming its farewell into the void. Even in the crowded cosmos, some gamma-ray bursts prefer solitude. Take GRB 150518A, a burst that erupted 6.5 billion light-years away, not unusual in itself until astronomers searched for its home. Instead of finding a bustling galaxy, their telescopes revealed nothing, just an empty patch of space, as if the burst had appeared out of pure void. Scientists dubbed it the cosmic hermit, an explosion without an obvious home, drifting alone in the interstellar darkness like a campfire lit in the middle of a desert. So how does a GRB typically born from massive stars end up in no man's land? One theory points to galactic ejections, where stars get flung into deep space like cosmic outcasts. Imagine a stellar game of pinball. When two galaxies collide, their gravitational chaos can slingshot stars at blistering speeds, sending them careening into the void with no return ticket. If one of these exiled stars later collapsed into a gamma-ray burst, we'd see exactly what GRB 150518 showed, an explosion with no galaxy in sight. It's like finding a charred matchstick in an empty field, the last trace of a wanderer who vanished long ago. But there's a twistier possibility. Dark matter might be hiding the burst's true origins. Some galaxies, especially faint dwarf ones, are so dominated by dark matter that their starlight barely registers. If GRB 150518 are erupted in one of these ghostly halos, our telescopes could miss the host entirely, glimpsing only the burst itself, a flare from a shadowy cosmic neighborhood. Picture a lighthouse on a foggy night. You'd see the beam, but not the island it's anchored to. The intrigue deepens when you consider rogue stars, stellar nomads that drift between galaxies after being torn loose by tidal forces. These lone wolves account for up to half the stars in some galaxy clusters, and if one happened to be massive enough to produce a GRB, its explosion would appear orphaned, a cosmic mystery with no address. It's the astronomical equivalent of hearing a gunshot in the woods but finding no shooter, just echoes fading into the trees. What makes this lonely burst so compelling isn't just its isolation, but what it says about the universe's unseen landscapes. For every GRB we spot in a glittering galaxy, there might be others lurking in the darkness, explosions from stars that slip their gravitational tethers or galaxies too faint to detect. GRB 150518 forces us to question our assumptions. Is space truly empty where we see nothing, or are we just missing the signs? And perhaps most poetically, this hermit burst might be the exception that proves the rule. Even in the vast, crowded universe, some things still choose to go it alone, leaving behind only a fleeting flash, a question mark written in gamma rays, and the haunting possibility that the cosmos still holds secrets we've only begun to trace. Some gamma-ray bursts do more than shatter distance records. They illuminate the universe's darkest chapter, a shadowy era known as the reionization epoch. Picture a cosmos barely out of its infancy. 500 million years after the Big Bang, the first stars flicker to life in a sea of neutral hydrogen gas. Their ultraviolet radiation begins stripping electrons from atoms, burning away the cosmic fog like sunlight evaporating morning mist. Until recently, this pivotal transition was theoretical, a hazy period astronomers struggled to observe. Then came GRB 130606A, a burst so distant its light carried chemical fingerprints from the universe's first billion years. Detected in June 2013, this explosion erupted when the cosmos was just 930 million years old, making it one of the farthest GRBs ever seen. But its real value lay in the afterglows spectrum, a rainbow of absorbed light revealing the composition of ancient gas clouds. As that light traveled toward Earth, it passed through pockets of intergalactic hydrogen, imprinting telltale dips in specific wavelengths. These absorption lines became a cosmic barcode, allowing scientists to measure the gas's ionization state. How much had been cooked by early starlight versus still pristine neutral hydrogen? The findings were revelatory. GRB 130606A spectrum showed a patchwork universe, with some regions already ionized while others remained stubbornly opaque. It was like mapping the edges of a wildfire, tracing where the flames of starlight had and hadn't yet spread. Even more surprising was the burst's host galaxy. Despite its youth, it contained traces of heavier elements like carbon and silicon, proof that generations of stars had already lived, died, and seeded the cosmos with metals before reionization completed. This burst also exposed the violent nature of the early universe. The same galaxies birthing the stars that cleared the cosmic fog were also producing GRBs at rates 10 times higher than today. Every flash was a double-edged sword, a beacon marking star formation's progress, but also a testament to the chaotic, short-lived nature of the universe's first stellar giants. They lived fast, died young, and left behind bursts bright enough to pierce the lingering hydrogen fog, a fog their very existence helped dissolve. What makes GRBs like this one indispensable is their ability to probe regions traditional telescopes can't. Quasars' bright galactic cores, often used to study reionization, only illuminate narrow beams, like shining a flashlight down a hallway. GRB, by contrast, backlight everything along their line of sight, offering panoramic views of the early cosmic web. It's the difference between studying a forest by spotlighting one tree versus capturing the entire canopy at sunrise, and the implications stretch even further. The burst spectrum contained hints that reionization wasn't uniform. Some cosmic neighborhoods cleared faster than others, perhaps due to clusters of particularly massive stars or early galaxy mergers. These variations could explain why different experiments sometimes clash on exactly when reionization ended. GRB 130606 became a Rosetta Stone, helping translate between conflicting data sets by showing that the answer might depend on where and how you look. So while this ancient burst lasted mere seconds, its legacy endures. It gave us front-row seats to the universe's grand awakening, the moment starlight first began sculpting the cosmos into the transparent expanse we know today. And with every new ultra-distant GRB discovered, we add another piece to the puzzle, slowly revealing how darkness gave way to light, one cataclysmic flash at a time. The universe saves some of its strangest gifts for last. Case in point, GRB 101225A, a gamma-ray burst so bizarre, astronomers nicknamed it the Christmas burst. Detected by NASA's Swift satellite on December 25, 2010, this explosion 5 billion light-years away should have faded within hours like every other GRB. But instead of vanishing, its afterglow pulsed and flickered for 28 straight days, like a cosmic tree refusing to take down its holiday lights. This wasn't just unusual behavior. It defied every textbook model of stellar explosions, forcing scientists to consider scenarios straight out of a sci-fi novel. One radical theory involved a neutron star playing cosmic Pac-Man. Imagine a massive comet or small planet spiraling too close to this dense stellar corpse. As tidal forces shredded the object into a stream of debris, the neutron star's gravity would have compressed the material into a swirling disk, superheating it until it detonated in a series of eruptions. Each time a fresh chunk of debris fell onto the star's surface, it would have ignited another burst of energy, like throwing logs on a fire, but with the violence of a thermonuclear blast. The result, a light curve that didn't crash after the initial spike but roller-coasted for weeks, its flickers tracing the feast of a star consuming its own cosmic wreckage. Animations of the Christmas burst's light curve tell the story better than words. Where typical GRBs show a sharp peak followed by a smooth decline, this one's graph looks like a seismograph during an earthquake, spikes upon spikes, as if the explosion kept reigniting itself. Some models suggest we weren't seeing one cataclysm but a chain reaction. First, the neutron star's magnetic field trapped infalling debris in an unstable orbit. Then chunks of matter collided at relativistic speeds, sparking secondary explosions that lit up like firecrackers along a fuse. It's the celestial equivalent of a car crash, followed by the gas tank exploding, then the tires, then the hood, all in slow motion across a month of cosmic time. Yet the comet-neutron star collision isn't the only explanation. Another camp argues the Christmas burst might have been a supernova chameleon, where a dying star's core collapse triggered a gamma-ray jet pointed just slightly away from Earth. What we interpreted as a prolonged afterglow could have been the supernova's shockwave finally catching up to the jet's debris, lighting it up like a delayed fireworks finale. Or perhaps the burst's jet plowed through an unusually thick cloud of interstellar gas, creating turbulence that extended the afterglow's lifespan like a car's taillights glowing longer in dense fog. What makes this burst unforgettable isn't just the mystery, it's the timing. landing on Christmas Day, it felt like the universe had wrapped astronomers a puzzle they're still unwrapping 14 years later. Every tweak to the models, every new simulation brings fresh insights into how neutron stars interact with their environments, how supernova can masquerade as GRBs, and how even the most well-studied cosmic phenomena can still deliver jaw-dropping surprises. The Christmas burst reminds us that for all our telescopes and supercomputers, the cosmos still keeps a few tricks up its sleeve ready to dazzle us when we least expect it. We're on the verge of a revolution in how we witness gamma-ray bursts, one where we won't just see these cosmic explosions, but feel them ripple through the fabric of space itself. The next generation of gravitational wave observatories, like the Laser Interferometer Space Antenna LISA and the Einstein Telescope, promise to detect GRB progenitors so distant their light hasn't even reached us yet. Imagine catching the tremors of two neutron stars colliding 12 billion light-years away, an event so ancient it unfolded when the universe was still in diapers. Here's how it'll work. Current detectors like LIGO and Virgo can spot gravitational waves from mergers within a few 100 million light-years. But LISA, set to launch in the 2030s, will operate in space with laser arms spanning millions of kilometers, making it sensitive to lower frequency ripples from mergers at cosmic distances. Pair that with the Einstein telescope's underground precision, and suddenly, we're not just hearing the universe's drumbeats, we're tuning into its deepest, oldest echoes. A neutron star collision 12 billion light-years away would send gravitational waves surfing across expanding space for eons, stretching their wavelengths but preserving their secrets. By the time they reach us, those waves could reveal details about the star's masses, spins, and even the universe's expansion rate at that primordial era. But here's the real magic. These observatories might catch mergers before their gamma rays arrive. Gravitational waves travel unhindered through gas and dust, while gamma rays can scatter or lag behind. It's like feeling an earthquake seconds before hearing the thunder. If LISA picks up a distant merger signal, telescopes could swing into position, waiting for the gamma-ray encore, a celestial early warning system that lets us watch GRBs in real time, from gravitational birth to electromagnetic fireworks. And the data won't just be about distance. The shape of the gravitational waves could expose whether the collision birthed a black hole straight away or left behind a temporary magnetar, a detail gamma rays alone can't always confirm. It's like comparing an X-ray to a fingerprint. One shows the aftermath, the other the exact moment of transformation. This isn't just about breaking records. Detecting mergers from the universe's first billions of years would test whether neutron stars formed differently back then, perhaps with exotic quark matter cores or stronger magnetic fields. Each ripple becomes a time capsule, carrying whispers from an epoch when the cosmos was forging its first heavy elements in the kilns of colliding stars. So while today's GRB hunters rely on gamma rays and afterglows, tomorrow's might navigate by spacetime's subtle shudders, tracing the universe's most violent dances from the shadows they cast on the void itself. And when that first ultra-distant merger signal arrives, it won't just be a detection. It'll be a message from the cosmic dawn, written in ripples we've only just learned to read. Sometimes the universe hands astronomers a free telescope, one crafted from galaxies themselves. Take GRB 000131, a burst so distant its light took over 12 billion years to reach us. Normally, an explosion that old would be barely visible, its glow stretched thin by cosmic expansion. But this burst got a lucky break. Its light passed directly through a massive galaxy cluster on its way to Earth, bending and brightening like sunlight through a magnifying glass. Scientists call this the dusty lens effect, where entire galaxies act as natural telescopes, amplifying flashes from the universe's edge. The mechanics are straight out of Einstein's playbook. According to general relativity, massive objects warp space-time, creating gravitational wells that deflect passing light. When a galaxy cluster sits between us and a distant GRB, its combined gravity bends the burst's light rays, funneling them toward Earth like a cosmic spotlight. The result, a burst that appears 10 to 100 times brighter than it would otherwise, a fleeting gift from the universe's own optics. For GRB 000131, the intervening cluster boosted its visibility enough to make detailed spectroscopy possible, revealing chemical fingerprints from an era when galaxies were still assembling. But gravitational lensing isn't just about brightness, it's about magnification. The same effect that brightens the burst also stretches its afterglow into distorted arcs or multiple images, like reflections in a funhouse mirror. In 2011, Hubble caught one such lens GRB split into 4 copies by a foreground galaxy, each image arriving at slightly different times due to the varied paths its light took around the lens. It's as if the cosmos staged its own rerun, broadcasting the same explosion from 4 angles across space-time. These natural telescopes have unique advantages over human-built ones. Unlike our instruments, which struggle to focus on the faintest objects, gravitational lenses don't discriminate by distance. They amplify anything perfectly aligned behind them, whether it's 5 billion or 13 billion light-years away. They even correct for cosmic expansion's dimming effect, letting us peer deeper into the early universe than technology alone allows. It's like turning every galaxy cluster into a makeshift observatory, each one capable of revealing bursts we'd otherwise never spot. Of course, there's a catch. Dust within the lensing galaxies can absorb or scatter the very light they're magnifying, particularly at blue wavelengths. That's why some lens GRBs, like GRB 060202, showed unusually red afterglows. Their shorter wavelength light got filtered out by cosmic soot. Astronomers must account for this dusty component when interpreting spectra, separating the burst's true colors from the lens's smudges. Yet even with these quirks, lens GRBs offer something irreplaceable, a chance to study the universe's youth in HD. By leveraging nature's magnifying glasses, we've glimpsed star-forming regions in galaxies born just a billion years after the Big Bang, traced the distribution of dark matter in lensing clusters, and even tested whether fundamental constants like the speed of light have changed over cosmic time. Every lensed burst is a 2-for-1 deal, a flash from the cosmic dawn, and a free masterclass in how gravity shapes our view of the universe. So the next time a GRB flares impossibly bright, remember, it might not be the burst itself that's extraordinary, but the invisible cosmic lens hanging in the darkness between us, twisting space-time into a temporary window to the past. Gamma-ray bursts come in 2 flavors, short and long, and their preferred cosmic neighborhoods couldn't be more different. Short bursts born from the violent mergers of neutron stars tend to be homebodies, typically flaring up around 6 billion light-years away. That's practically next door compared to their long-duration cousins, which often erupt from the universe's frontier, up to 13 billion light-years distant. This split isn't random, it's a direct consequence of how these explosions form. Neutron star mergers require galaxies mature enough to have forged these dense stellar corpses, then patiently waited for their slow gravitational dance to culminate in catastrophe. That means short GRBs often trace the universe's middle age, when galaxies had enough time to cook up neutron stars but hadn't yet scattered them too far apart. Long GRBs, on the other hand, are the domain of cosmic youth. These explosions mark the deaths of massive, fast-burning stars, the kind that thrived when the universe was just a few billion years old, during the heyday of star formation. Back then, galaxies were churning out short-lived hypergiants at breakneck speed, creating perfect conditions for frequent core collapse explosions. This explains why the most distant GRBs on record are almost exclusively long bursts. Their progenitor stars didn't just live fast and die young, they did so when the cosmos itself was still young. Redshift graphs paint this divide in stark color. Plot short GRBs on a redshift distribution chart, and you'll see a bell curve peaking around redshift 0.5, corresponding to distances of about 5 to 7 billion light-years. Long GRBs stretch that curve to the right, with a long tail extending past redshift 8 distances so vast, the universe was less than 700 million years old when those bursts detonated. It's like comparing the population density of a modern city to a frontier settlement. One shows maturity, the other wild, untamed proliferation, but there's a twist. Occasionally, a short GRB defies expectations by appearing unexpectedly deep in the cosmic past. Take GRB 210426a, a short burst detected at redshift 1.9, roughly 10 billion light-years away. Its existence suggests some neutron stars might have merged far earlier than models predict, perhaps in unusually dense young galaxies where stellar encounters were more frequent. These outliers are cosmic rule breakers, proving that even the clean divide between short and long GRBs has blurry edges. What makes this distance dichotomy so valuable is how it turns GRBs into cosmic archaeologists. Short bursts act as probes for the universe's adolescence, when galaxies were settling into stable structures. Long bursts, by contrast, excavate the infant era, when the first stars were transforming primordial gas into the building blocks of everything we see today. Together, they form a timeline written in gamma rays, each type marking a different chapter in the story of how our universe grew up. And with every new burst detected, we sharpen that timeline, filling gaps in our understanding of when and where the cosmos chose to unleash its most spectacular fireworks. Some gamma-ray bursts come with a cosmic mystery. They explode like fireworks but leave no trace of the expected grand finale. GRB 060505 is a perfect example, a burst that detonated 1.3 billion light-years away but left astronomers staring at empty sky where a supernova should have been. Normally, long GRBs signal the death of massive stars, with a brilliant supernova tagging along like an encore. But when telescopes trained on this burst host galaxy for weeks, the supernova never showed. It was as if a magician had vanished without leaving even a puff of smoke. So where did the star go? One possibility is the failed supernova scenario, a cosmic dud where a massive star collapses straight into a black hole without the usual explosive fanfare. Instead of rebounding in a supernova shockwave, the star's core might have imploded so abruptly that the outer layers got swallowed whole, like a collapsing building vanishing into its own sinkhole. No outer explosion, no lingering glow, just silence where there should have been light. This would make GRB 060505 a stellar tombstone with no epitaph, a memorial to the star that disappeared without saying goodbye. Another theory points to stars born with unusual compositions, those forged in the early universe's metal-poor environments. Without heavier elements to help drive the explosive chemistry of a supernova, these stars might implode more efficiently, their cores turning directly into black holes while their outer layers get sucked into oblivion. It's the cosmic equivalent of a firework fizzling out before ignition. It's gunpowder packed too tight to burst, but the plot thickens. Some researchers argue the missing supernova might not be missing at all, just hiding in plain sight. If the GRB's jet was pointed directly at Earth, the afterglow could have outshone a dim supernova, masking it like a spotlight drowning out a candle. Alternatively, dust in the host galaxy might have absorbed the supernova's visible light, leaving only infrared whispers that older telescopes couldn't detect. What makes this missing supernova problem so fascinating is how it forces us to rethink stellar life cycles. If massive stars can bypass supernova entirely, collapsing silently into black holes, it means our census of cosmic explosions could be missing entire categories of stellar death. Every GRB without a supernova counterpart becomes a clue, hinting at the universe's quieter vanishing acts, the stars that disappear without applause, their final moments known only by the gamma-ray echo they leave behind. Perhaps future observations will uncover more of these ghostly collapses, revealing a hidden population of stars that slip into darkness unnoticed. Until then, bursts like GRB 060505 remain cosmic riddles, reminding us that even the brightest explosions can have the darkest secrets. At the edge of the observable universe, where time itself seems to fold backward, gamma-ray bursts occasionally cross paths with quasars, the universe's first monsters. GRB 080913 is one such cosmic oddity, a burst detected 12.8 billion light-years away, nestled suspiciously close to a supermassive black hole blazing as a quasar. With a redshift of 6.7, this explosion erupted when the universe was just 860 million years old, a chaotic era when the first galaxies were still assembling around voracious black holes. That proximity isn't just coincidence, it might be a clue to one of the rarest GRB triggers of all, a black hole's appetite turning deadly. Most gamma-ray bursts stem from collapsing stars or neutron star collisions, but theorists have long speculated about an exotic third category, active galactic nucleus or AGN-triggered bursts. Picture a supermassive black hole at a galaxy's core, its gravitational pull so fierce it shreds passing stars into spaghetti like streams of gas. Occasionally, one of those stars might be a massive, rapidly spinning Wolf-Rayet star, a prime GRB progenitor. As the black hole's tides stretch and compress the star, the resulting instability could ignite a gamma-ray jet alongside the usual quasar flare. It's the cosmic equivalent of a volcano erupting during an earthquake, two disasters colliding in a single catastrophic event. GRB 080913's host environment makes this scenario plausible. The burst occurred in a galaxy already hosting a hyperactive quasar, its central black hole guzzling matter at a ferocious rate. While most young galaxies in this era were just igniting their first stars, this one had already built a behemoth, a black hole weighing perhaps 1 billion suns. Such extreme conditions could yank stars from their orbits and rip them apart near the black hole's poles, where magnetic fields might then funnel stellar debris into the narrow jets needed for a GRB. What's tantalizing is how little we know. Only a handful of GRBs have been found this deep in cosmic history, and fewer still near quasars. Each one could be a Rosetta Stone, decoding how supermassive black holes influenced their galaxy's evolution. Did these early monsters catalyze GRBs by disturbing stellar orbits? Or did GRBs themselves seed the heavy elements that helped black holes grow? The answers might lie in the light curves of bursts like GRB 080913, where subtle fluctuations could betray the hand of a lurking giant. And here's the twist: if AGN-triggered GRBs exist, they'd pack unique signatures. Unlike typical bursts, their jets might carry traces of the black hole's magnetic field, imprinting telltale polarization patterns on the gamma rays. Their afterglows could last longer, fueled by ongoing accretion from the quasar's disk. Some might even arrive with gravitational wave counterparts, as the black hole's gravity stirs spacetime while devouring its stellar victim. For now, GRB 080913 remains an enigma, a flash from the abyss caught between the birth of galaxies and the awakening of their black hole hearts. But as telescopes probe deeper into the cosmic dawn, every new detection brings us closer to answering whether the universe's most luminous explosions and its hungriest monsters sometimes work in tandem, rewriting the rules of stellar life and death in the process. Some gamma-ray bursts refuse to play by the rules, especially when they linger long after their expected expiration date. Take GRB 060614, a burst that shattered expectations by behaving like two explosions in one. Detected 1.6 billion light-years away, this event began like a textbook short GRB lasting under 2 seconds, but then defied classification by emitting faint gamma rays for nearly 100 seconds more. This extended emission turned a seemingly straightforward neutron-star merger into an astrophysical whodunit, forcing scientists to question whether some bursts might blur the line between different explosion mechanisms. What makes this burst so puzzling is the stark contrast between its initial spike and the drawn-out aftermath. Short GRBs typically flare up and vanish like camera flashes, their brief duration reflecting the rapid death spiral of colliding neutron stars. Long GRBs, born from collapsing massive stars, often show sustained emission as the dying star's core continues feeding energy into the jet. GRB 060614 did neither, or perhaps both. Its initial milliseconds matched a merger's profile, but the prolonged tail mimicked a collapse event, as if the universe couldn't decide which script to follow. Theories abound to explain this hybrid behavior. One camp argues these bursts could be failed supernova, where a massive star's core collapses directly into a black hole without the usual explosive rebound, producing a short-lived jet before residual debris falls in, powering the extended emission. Others propose a neutron-star merger where the remnant, perhaps a rapidly spinning magnetar, briefly resists becoming a black hole, its magnetic field squeezing out extra energy like a cosmic toothpaste tube. There's even speculation that some mergers might involve exotic stellar remnants like quark stars, objects so dense they straddle the boundary between neutron stars and black holes, potentially explaining the dual-phased energy release. Adding to the mystery, GRB 060614's host galaxy deepened the enigma. Most short GRBs occur in galaxies where star formation peaked billions of years ago, but this one erupted in a region with recent stellar births, an environment more typical of long GRBs. It's like finding a Viking artifact in a modern city. The context doesn't match the expected timeline. This anomaly suggests that either our classification system is oversimplified, or that some GRB progenitors can form through multiple pathways, their explosions adapting to local conditions. The debate rages because the stakes are high. If even a fraction of short GRBs show extended emission, it could mean mergers and collapses sometimes produce eerily similar signatures, complicating efforts to use GRBs as cosmic distance markers or probes of neutron star physics. Alternatively, these hybrid bursts might represent an entirely new class of cataclysms, events where the universe mixes and matches its most violent recipes. For now, GRB 060614 remains a cosmic Rosetta Stone, its dual-language light curve waiting to be fully deciphered. With each new detection of extended emission, astronomers edge closer to understanding whether they're witnessing the universe's exceptions or discovering rules they never knew existed. Living in the Milky Way comes with hidden risks, including the slim but terrifying possibility that a gamma-ray burst could one day sterilize our planet. Statisticians have run the numbers, and the results are both unsettling and oddly reassuring. For a GRB to pose an existential threat to Earth, two cosmic dice must roll in perfect unison. The burst must occur within our galaxy, and its deadly jet must point directly at us. The odds, approximately 1 in 10 million per century, like waiting for a specific grain of sand to fall in an hourglass the size of our solar system. Let's break down the math. Milky Way-sized galaxies typically host one long GRB every 100,000 years, but crucially, these jets are pencil-thin, covering just a fraction of a percent of the sky. Even if one erupted in our galactic backyard, the chance it's aimed Earthward is vanishingly small. To trigger mass extinction, models suggest a GRB would need to strike within 6,000 light-years, close enough for its gamma rays to shred our ozone layer, unleashing deadly ultraviolet radiation and climate collapse. That's roughly the distance to the Crab Nebula, putting a worrisome bullseye on nearby star-forming regions like Orion. Yet history offers perspective. In 1998, GRB 980425 became the closest recorded burst at a safe 140 million light-years. Had it occurred within our galaxy, say 6,000 light-years away, its energy would have bathed Earth in radiation equivalent to 1,000 atomic bombs detonating per square kilometer. The after-effects: global ozone depletion up to 50%, acid rain, and a years-long cosmic winter as gamma rays transformed atmospheric nitrogen into smog like nitrogen dioxide. Compared to asteroids or supervolcanoes, it's the ultimate blindsided catastrophe. No warning, no debris, just an invisible surge of photons rewriting the chemistry of life itself. But here's the twist that lets astronomers sleep at night. GRB 980425's host galaxy is a chaotic metal-poor dwarf, a far cry from the Milky Way's orderly spiral. Our galaxy's higher metal content actually suppresses GRB formation. Heavy elements stabilize massive stars, making them less prone to the violent collapses that trigger these jets. Statistically, we're 30 times safer here than if we orbited a galaxy like the burst's original home. It's the cosmic real estate equivalent of choosing a quiet suburb over a supernova alley. The real comfort lies in time scales. Even if a Milky Way GRB did line up its crosshairs, we'd likely have millennia of warning. Future telescopes could map potential progenitor stars Wolf-Rayet behemoths simmering on the brink of collapse. And should one erupt, its neutrinos would arrive hours before the gamma rays, offering a sliver of time to prepare. For now, the numbers are on our side. The universe may be violent, but in this galactic neighborhood, the odds of a lethal strike are reassuringly long. A cosmic game of Russian roulette with 1,000,000 chambers and only one bullet. Gamma-ray bursts are masters of cosmic deception, capable of creating illusions that defy common sense. One of their most mind-bending tricks involves jets that appear to move faster than light, an impossibility according to Einstein's relativity. Take GRB 030329, a burst 2 billion light-years away whose afterglow seemed to show jet fragments racing outward at 7 times light speed. This isn't science fiction breaking loose. It's a spectacular trick of perspective called superluminal motion, where reality and perception part ways in the theater of extreme physics. Here's how the illusion works. When a GRB's jet barrels toward Earth at over 99.9% light speed, its material almost chases the very light it emits. Imagine a spaceship flying nearly as fast as its headlights. If the ship approaches you, each new pulse of light has less distance to travel, making the ship appear to arrive sooner than expected. Similarly, as matter in the jet surges forward, the time delay between light emitted from its advancing front and trailing end compresses dramatically. This creates the illusion that the jet's features are outpacing light itself, like a cosmic speedometer stuck in the red. Animations of relativistic jets reveal the mechanism in action. Picture a flashlight sweeping across a distant wall. If the beam moves fast enough, the illuminated dot can appear to travel faster than light, even though no physical object is breaking the speed limit. GRB jets exploit this same principle, their high-speed twists and knots producing apparent motion that's pure geometry rather than true velocity. What we're seeing isn't matter violating relativity, it's light playing tricks with arrival times, a celestial sleight of hand made possible by the jet's blistering speed and our privileged viewing angle. The implications reach beyond visual spectacle. By measuring these superluminal mirages, astronomers can calculate a jet's true velocity and geometry. GRB 030329's phantom sevenfold light speed motion, for instance, implied a real velocity of 0.99995 times light speed, a value so precise it helped confirm that GRB jets operate under physics' strictest rules even when they look lawless. These measurements also reveal how narrowly focused the jets must be. To produce such extreme illusions, they can't fan out more than a few degrees, or the effect would unravel like a magician's failed trick. Yet the wonder doesn't stop there. Superluminal motion offers a rare test of how matter behaves at nature's ultimate speed limit. The jet's ability to maintain such tight, stable beams across billions of light-years hints at unseen forces, perhaps immense magnetic fields acting like cosmic collimators or shock waves that keep particles aligned as they surf the wave of a stellar explosion. Every illusory burst of faster-than-light motion is really a breadcrumb trail leading back to the jet's hidden physics, written in the language of misdirection. So while GRBs might flirt with the impossible, they never truly break the rules. They simply remind us that the universe has a flair for drama, dressing its most violent acts in costumes of paradox. And in that tension between what we see and what's real, there's a lesson. Sometimes the most extraordinary truths hide behind the simplest illusions. Time is everything when it comes to decoding gamma-ray bursts, and sometimes just 2 seconds can separate the birth of a black hole from the death of a star. Astronomers discovered early on that GRBs fall into 2 distinct categories based on duration, with that critical divide set at exactly 2 seconds. Anything shorter typically signals the merger of 2 neutron stars, a hyperviolent collision that unleashes gravitational waves alongside gamma rays. Anything longer usually marks the collapse of a massive star, a supernova's fiery finale compressed into a beam of pure energy. This split isn't arbitrary, it's written in the physics of cosmic catastrophe. Histograms of GRB durations tell the story visually. Plot every known burst on a timeline, and you'll see a clear valley around the 2-second mark, like a cosmic sorting hat separating the brief from the prolonged. Short bursts cluster sharply under 2 seconds, their light curves spiking and vanishing like a camera flash. Long bursts stretch across the chart, some lasting minutes, their emission lingering as the dying star's core continues feeding energy into the jet. But outliers blur these boundaries. Bursts like GRB 060614, which began as a short event but dragged on for over 100 seconds, defying simple classification. The origins of this divide trace back to the engines powering each explosion. Short bursts stem from neutron star mergers, where 2 ultra-dense stellar corpses spiral together in a gravitational death grip. Their collision happens fast, fuel exhausted in seconds as the stars shatter into a black hole. Long bursts, by contrast, draw energy from collapsing massive stars, whose cores implode more gradually, like a building collapsing floor by floor. The star's outer layers take longer to funnel into the jet, stretching the burst's duration far beyond 2 seconds. Distance adds another layer to this split. Among the most distant GRBs, those erupting over 10 billion light-years away, almost all are long bursts. That's because the early universe thrived on massive, fast-burning stars, the perfect progenitors for prolonged explosions. Short bursts requiring the slower tango of neutron star mergers tend to appear closer in galaxies that had time to forge and pair these dense remnants. Yet even here, exceptions exist. GRB 210426a, a short burst over 10 billion light-years away, suggests mergers could happen earlier than models predicted, perhaps in regions of intense stellar crowding where neutron stars found partners faster. What makes the 2-second rule so powerful is how reliably it links burst duration to physical cause. When LIGO detects gravitational waves from a neutron star merger, astronomers can scan the skies for a matching short GRB and vice versa. When telescopes catch a long burst's afterglow, they know to search for the supernova that should follow. It's a cosmic fingerprint system where time itself becomes a clue to the explosion's origins. Yet the outliers keep us questioning. Why do some bursts straddle the divide? Could there be hybrid progenitors collapsing stars with neutron star companions, or mergers that briefly revive as magnetars? Each anomaly reminds us that the cosmos rarely fits neat categories, and that even a rule as steadfast as the 2-second divide has room for the universe's creativity. One thing's certain, when the next burst lights up the detectors, its duration will be the first clue in decoding whether we're witnessing a stellar collision or a star's last defiant scream. Astronomers expect gamma-ray bursts to leave cosmic breadcrumbs, an afterglow, a host galaxy, something to mark where the explosion occurred. But GRB 070125 broke all the rules. Detected 6 billion light-years away, this burst should have been anchored to a visible galaxy, yet when telescopes scoured its location, they found nothing but darkness. No spiral arms, no glowing stellar nurseries, just an empty stretch of sky where a cosmic detonation had moments before announced itself. This was no ordinary burst, it was a cosmic ghost, a flash without a home, and its mystery forced scientists to reconsider where stars live and die. One explanation points to the universe's shadowy suburbs, dark dwarf galaxies. These are tiny, faint collections of stars, often with 1,000 times less mass than the Milky Way, and so dim that even our best telescopes struggle to spot them. Unlike their brighter cousins, dwarfs are rich in primordial gas but poor in heavy elements, exactly the kind of environment where massive, fast-burning stars, the kind that produce long GRBs, might form. If GRB 070125 erupted in one of these cosmic back alleys, its host could easily evade detection like a firefly hidden in a fog bank. But there's an even stranger possibility. Some stars don't belong to galaxies at all. Gravitational chaos colliding galaxies, tidal forces, or close encounters with black holes can fling stars into the void, leaving them to wander intergalactic space like cosmic nomads. These rogue stars are thought to number in the trillions, drifting between galaxies in a sea of near-perfect blackness. If one of these outcasts was massive enough to collapse into a GRB, its explosion would appear utterly isolated, a beacon with no lighthouse. The intrigue deepens when you consider the burst's afterglow. Unlike some hostless GRB whose light might be obscured by dust, GRB 070125's afterglow was bright and unobstructed, ruling out the usual excuses for a missing host. Spectra revealed no traces of interstellar gas from a galaxy, no chemical fingerprints of a stellar neighborhood. It was as if the burst had erupted in a perfect vacuum, challenging our understanding of where and how stars form. Could this be evidence of an entirely new class of GRB progenitors, stars born in the absolute wilderness, far from any galaxy? Or does it hint at galaxies so faint, so diffuse, they redefine what we consider a cosmic structure? Every time a telescope fails to find a host, it chips away at our assumptions, reminding us that the universe is far stranger than our categories allow. For now, GRB 070125 remains an enigma, a cosmic question mark written in gamma rays. But its very existence is a clue that the universe's story is still being written, and some of its most dramatic chapters may be unfolding in the darkness between the stars. Rising like colossal chimneys from the Milky Way's heart, the Fermi bubbles stretch 25,000 light-years above and below our galaxy's disk. Twin towers of gamma-ray glow that hint at a cataclysm we barely missed. Discovered in 2010 by NASA Fermi telescope, these gargantuan structures bear an eerie resemblance to scaled-down gamma-ray burst remnants, as if our galaxy survived its own miniature GRB event millions of years ago. Their sheer scale defies imagination. Each bubble could swallow our entire local group of galaxies, yet they're invisible to human eyes, radiating only in the high-energy light that betrays their violent origins. The leading theory suggests these bubbles are scars from our supermassive black hole, Sagittarius A, going through a violent feeding frenzy. Imagine the black hole gorging on a wayward gas cloud or star, belching out twin jets of relativistic particles that inflated these cavities like cosmic balloons. What makes this fascinating is the energy involved, equivalent to 100 supernova detonating simultaneously. While not as apocalyptic as a full GRB, such an outburst would have been the Milky Way's most violent event since its formation, flooding the galactic center with enough radiation to sterilize nearby star systems. But here's where the GRB connection gets spine-tingling. the bubble's gamma-ray spectra share uncanny similarities with the afterglows of distant jet-driven bursts. Both feature telltale signatures of particles accelerated to near light speed, tangled magnetic fields, and shock waves rippling through thin plasma. It's as if nature took the blueprint for a GRB's relativistic jet and dialed down the power, creating a galactic-scale echo of those universe-shaking explosions. Some theorists even speculate that Sagittarius might have unleashed a proper GRB-like jet in the distant past, one pointed safely away from Earth's orbital plane, leaving only these bloated remnants as a cryptic warning. Supporting this idea are the bubbles, cocoons, filaments of X-ray emission wrapped around their bases like cosmic scar tissue. These structures mirror the turbulent aftermath seen in GRB host galaxies, where jets plow through interstellar material, leaving heated trails in their wake. The Milky Way's version appears more sedate, but the physics might be fundamentally similar. Relativistic particles slamming into galactic gas, creating shock fronts that glow for epochs. Yet mysteries linger. The bubble's edges are suspiciously sharp, as if something prevented their energy from dissipating, perhaps a galactic magnetosphere or dark matter halo. Their symmetry is equally puzzling, suggesting the outburst was unnervingly precise, like a surgical gamma-ray laser fired perfectly perpendicular to our galaxy's disk. And their age, estimates range from 2 to 10 million years, a blink in cosmic time that means our early human ancestors might have witnessed the afterglow as an eerie, diffuse light in the night sky. What's certain is this: if a similar event occurred today, even at reduced GRB-scale energies, the consequences would be dire. A jet pointed inward could irradiate the galactic disk, triggering mass extinctions across thousands of light years. It's a reminder that our galaxy isn't just a static backdrop, it's a dynamic engine capable of its own brand of violence, one that leaves behind monuments like the Fermi bubbles as both warning and wonder. These structures challenge us to rethink black holes as not just destroyers, but artists, ones whose outbursts paint the cosmos with the same high-energy palette as the universe's most devastating explosions. Most gamma-ray bursts fade fast, their fury spent in seconds, their afterglows dimming to nothing within hours, but GRB 120422 broke the mold. Detected 4 billion light-years away, this burst didn't just flash and vanish. Its afterglow clung to brilliance like a dying ember refusing to go cold, maintaining a steady glow for nearly a full day. This wasn't just unusual, it was a direct challenge to our understanding of how GRBs work, pointing to a hidden engine still churning long after the initial explosion. At the heart of this mystery lies the concept of energy injection. Normally, a GRB's afterglow is powered by the explosion's shockwaves plowing into surrounding gas, like a snowplow lighting up as it rams through a blizzard. But GRB 120422A's stubborn glow suggested something more. A central engine, likely a newborn black hole or magnetar, still actively pumping energy into the debris field. Picture a car crash where the wreckage keeps exploding hours later because someone left the fuel line wide open. That's essentially what astronomers think happened here. A cosmic power source refusing to shut off, relentlessly feeding the afterglow with fresh particles and radiation. The data paints a vivid picture. While typical afterglows decay predictably, this one flatlined in brightness for 18 hours before finally fading. Spectroscopic analysis revealed something even stranger: the light's polarization. A clue to magnetic field geometry remained constant throughout the plateau, as if the engine's output was being funneled through a stable, long-lasting nozzle. That stability is key. Short-lived shocks can't maintain such consistency. Only an orderly, sustained energy source could explain it, like a fire hose left running at steady pressure instead of a single bucket of water dumped all at once. The implications ripple outward. If some central engines persist this long, it means GRBs aren't always one-off explosions, they can have afterburners. For magnetars, this might involve a delay as the star's powerful magnetic fields gradually break its rotation, converting spin energy into fresh particle acceleration. For black holes, it could mean prolonged accretion, a stellar corpse still disassembling itself and feeding the beast at its core. Either way, GRB 120422 proved that the universe's most violent explosions sometimes come with a hidden snooze button, stretching their farewell across hours instead of seconds. What makes this burst particularly valuable is its rarity. Only a handful of GRBs exhibit such clear plateau phases, making each one a Rosetta Stone for decoding central engine behavior. By comparing them, astronomers have begun piecing together a taxonomy of afterglows, some flickering like candle flames, others burning steady like pilot lights, each reflecting different engine lifetimes and power outputs. And with every new plateau detected, we get closer to answering the fundamental question: just how long can a dying star's heart keep beating after its body has been blown apart? For now, GRB 120422 stands as a testament to the universe's refusal to be simple. Even in death, some stars leave behind engines that defy expectations, their echoes lingering in the darkness long after the initial blast should have silenced them. And in those echoes, we find clues not just about how stars die, but about how the cosmos sustains its most extreme violence across time and space. We're standing at the edge of a cosmic revolution, one where we'll peer back to the universe's first starlight, witnessing explosions from stars so ancient they defy everything we know. The James Webb Space Telescope is about to rewrite the rules, hunting for gamma-ray bursts in the era of cosmic dawn, the first 500 million years after the Big Bang. This isn't just astronomy, it's time travel, with JWST infrared eyes acting as portals to an epoch when the universe was raw, unformed, and blazing with the first generation of stars. These weren't ordinary stars, born from pure hydrogen and helium without a trace of heavier elements. So-called population Roman 3 stars were titans hundreds of times the sun's mass, burning ferociously and dying young in colossal explosions. Theory predicts their deaths would unleash gamma-ray bursts unlike any we've seen, longer, brighter, and potentially lacking the chemical fingerprints of later stellar generations. The catch: their light, stretched by cosmic expansion, arrives as faint infrared whispers buried in the noise of the universe. Until JWST, we simply didn't have a telescope sensitive enough to dig them out. Simulations of these primordial explosions paint a surreal picture. Unlike modern GRBs, which leave behind afterglows rich in metals, population Roman 3 bursts might shine with eerie purity, their spectra devoid of carbon, oxygen, or ion lines. Instead, they'd carry the raw signature of hydrogen and helium alone, like a cosmic Rosetta Stone revealing the universe's original language. JWST could spot these bursts by their infrared afterglows, distinguishing them from younger GRBs through their unique lack of heavy elements. It's like finding a cave painting untouched by later civilizations, a pristine relic of the cosmos's first violent moments. But detecting these bursts is only half the battle. To confirm a population Roman 3 origin, astronomers will need to scrutinize the host environment, or rather, the lack thereof. These stars likely formed in miniature protogalaxies, tiny clumps of gas too faint for even JWST to see directly. Instead, the absence of a visible host galaxy could itself be the smoking gun, pointing to a burst from one of the universe's first stellar nurseries. Imagine spotting a wildfire in a pitch-black forest. The flames are visible, but the trees remain unseen. That's the challenge JWST faces, isolating bursts from voids where darkness speaks louder than light. The implications stretch far beyond GRBs. If JWST catches even one confirmed population Roman 3 burst, it would validate decades of theoretical models about the universe's first stars. Their existence, masses, and death mechanisms are all still hypothetical, grounded in math but lacking direct proof. A single detection could reveal whether these pioneers truly were the monsters simulations suggest, and whether their explosions seeded the cosmos with the first heavy elements, paving the way for everything that followed. And here's the kicker: JWST might not have to wait long. Some calculations suggest that if population Roman 3 stars died as GRBs at even a fraction of the rate of modern stars, the telescope could spot several per year. Each one would be a time capsule, carrying data from an era before galaxies, before planets, before chemistry as we know it. They'd illuminate not just how stars die, but how the universe itself transitioned from simplicity to complexity, from hydrogen and helium to the rich tapestry of elements that make our existence possible. This is the frontier where JWST power shines brightest. While Hubble gave us deep-field glimpses of early galaxies, JWST can pierce the veil of cosmic dawn itself, hunting for the flashes that mark the end of darkness. Every infrared photon from these bursts is a messenger from a time when the universe was new, when the first stars lived fast, died violently, and lit the fuse for everything to come. And with each observation, we're not just studying the past, we're uncovering the origin story of matter itself. Gamma-ray bursts don't always unleash their fury in a single, unified beam. Some fire off twin jets with startlingly different personalities. Take GRB 160625b, a burst 5 billion light-years away that stunned astronomers with its split personality outflow. Unlike typical GRBs that channel energy into a single relativistic jet, this one produced two distinct components: a narrow, ultra-fast spine of gamma rays surrounded by a slower, wider sheath of X-rays and optical light. It's as if the dying star couldn't decide between a surgical laser and a flamethrower, so it unleashed both at once. Here's where the cosmic fire hose analogy clicks. Picture a high-pressure nozzle with adjustable settings. Twist one way, and you get a concentrated stream capable of punching through concrete. Twist another, and it fans out into a broad spray. GRB 160625b's dual jets operate on similar principles, just scaled up to cosmic proportions. The inner jet, traveling at 99.9% light speed, carries the burst's hardest gamma rays like a particle accelerator focused to needlepoint. Meanwhile, the outer flow moves at a sluggish 90% light speed, dispersing its energy across a wider angle like the spray from a burst pipe. Together, they create a multi-layered blast, part precision strike, part shockwave that challenges our understanding of how stellar deaths sculpt their final outbursts. What makes this double jet structure so fascinating is how it solves a long-standing GRB puzzle. For years, astronomers struggled to reconcile bursts that produced both incredibly bright gamma-ray emission and unexpectedly luminous afterglows. Single jet models couldn't explain the full spectrum of observations until the dual-component idea emerged. By having two outflows operating at different speeds and energies, a single explosion can simultaneously produce the intense initial flash and sustain a prolonged afterparty across multiple wavelengths. It's like discovering that what we thought was a solo musician is actually a duet, with each performer hitting different notes to create a richer symphony. The physics behind this cosmic duet points to extreme magnetic drama. As the collapsing star's core forms a black hole or magnetar, its rotation and magnetic fields may become unstable, fracturing the jet into distinct layers. The inner jet could be powered directly by the central engine's spin, while the outer flow rides shockwaves from material colliding with surrounding gas. This creates a jet within a jet scenario where the two components interact like lanes of traffic merging at relativistic speeds. Spectroscopic data from GRB 160625b supports this. Polarization measurements revealed wildly different magnetic field alignments between the gamma ray and optical components, proving they originated from separate zones of the explosion. But the real kicker: these dual jets might be more common than we thought. Reanalysis of older bursts suggests many could have hidden secondary components masked by observational limits. It's like realizing every firework you've ever seen actually had an invisible second stage. You just needed the right tools to spot it. Future telescopes capable of simultaneous multi-wavelength observations could peel back these layers, revealing how often stars choose this two-tiered farewell. What's at stake goes beyond jet mechanics. If dual structures are widespread, they could explain why some GRBs appear oddly efficient at converting stellar mass into energy. The outer jet might be recycling shock energy that single jet models would miss. They could also influence how bursts enrich interstellar space with heavy elements, as the wider component disperses material differently than a pencil-thin beam. Every new dual jet detection rewrites the recipe for cosmic alchemy, proving that even in death, stars have more tricks up their sleeves than we ever imagined. So the next time a GRB flares in the darkness, remember, it might not be a solo act, but a coordinated strike from two cosmic forces, each playing its part in the universe's most violent encore. Gamma-ray bursts already push the limits of cosmic violence, but what if we told you the universe has a built-in energy cap, a ceiling that not even these cataclysms can breach? The numbers alone defy comprehension. The theoretical maximum energy for a GRB sits around 10 to the 55th ergs, a figure so vast it dwarfs the Sun's entire lifetime output by a factor of 100 billion. Yet here's the cosmic twist: despite scouring the skies for decades, we've never detected a burst even approaching that limit. The most energetic GRB ever recorded, the so-called brightest of all time event, topped out at a mere 10 to the 54th ergs, leaving physicists to wonder, is something or someone out there enforcing the universe's speed limit for destruction? This gap between theory and reality isn't just academic. It might hold clues to physics beyond Einstein, realms where quantum gravity and space-time itself behave differently. Picture the universe as an overworked power grid. Even in hypernova or neutron star mergers, the ultimate energy plants, there are only so many joules you can pump into a gamma-ray jet before the system overloads. Some theories suggest that at extreme energies, space-time's fabric begins to resist, like a rubber sheet stretching too thin. Particles that should accelerate to infinite energy instead hit a soft wall, their momentum dissipating into the quantum foam at scales a billion trillion times smaller than an atom. It's as if the cosmos has an undocumented safety protocol, preventing anything, even a dying star, from bending the rules too far. The implications ripple across cosmology. If GRBs truly can't breach the 10 to the 55th erg barrier, it could hint at exotic physics like Lorentz invariance violation, a crack in relativity's foundation where ultra-high-energy particles experience spacetime differently. Alternatively, the limit might reflect something more primal, the maximum energy a black hole's spin can impart to a jet before the system loses coherence. Imagine a whirlpool in water, spin it too fast and it collapses into chaos. Similarly, a black hole's ergosphere, the warped space just outside its event horizon, might only slingshot particles so efficiently before the jet frays at the edges. Yet the most tantalizing possibility is that we're seeing the fingerprints of quantum gravity. In theories like loop quantum cosmology or string theory, space-time isn't smooth at the tiniest scales. It's granular, like the pixels on a screen. Pump enough energy into a small volume, and those pixels might start to distort, imposing a natural energy ceiling. GRBs could be probing that threshold, their jets crashing against the universe's resolution limit like waves hitting a seawall. That would make every ultra-powerful burst a lab experiment at scales no collider could ever reach, testing whether space-time itself has a breaking point. So while we haven't yet spotted a GRB pushing the ultimate energy envelope, their absence speaks volumes. Each merely catastrophic burst is a reminder that even the cosmos has its guardrails, its unspoken laws written in gamma rays rather than ink. And somewhere out there, in the darkness between galaxies, the universe might be hiding its most violent explosions, not because they can't happen, but because the rules won't let them. Think of these 30 facts as cosmic postcards from the edge of space-time, each one stamped with the violence of a dying star, the birth cry of a black hole, or the whisper of a universe still taking shape. From gamma-ray bursts so bright they outshine entire galaxies, to explosions that forge gold in their wake, to flashes from the cosmic dawn that act as time machines to the first stars, we've journeyed through the extremes of existence. These aren't just distant fireworks, they're the universe's way of keeping a diary, etching its most pivotal moments into beams of light that cross billions of years just to reach us. Studying these bursts is like piecing together fragments of a grand cosmic puzzle. Every afterglow carries clues about how galaxies evolve, how elements spread, even how space-time itself behaves under conditions no lab could ever replicate. They reveal the universe's growing pains, its chaotic adolescence, its explosive creativity, and the invisible forces that stitch it all together. Whether it's the mind-bending illusion of jets appearing to break light speed, the eerie silence of orphan bursts without supernova, or the record breakers that push physics to its limits, each discovery rewrites what we know about the fabric of reality. And the most thrilling part, this is just the beginning, with telescopes like JWST probing deeper into the cosmic dark, and gravitational wave detectors tuning into spacetime's faintest ripples, we're on the verge of uncovering even more breathtaking secrets. The next gamma-ray burst could be the one that cracks open quantum gravity, proves the existence of primordial stars, or reveals a phenomenon we haven't even dreamed of yet. So here's your invitation to stay curious, because the universe isn't done surprising us. Now it's your turn. Which fact left you awestruck? Was it the burst that shook Earth's atmosphere, the ancient explosion we saw from 13 billion light-years away, or the eerie, dark bursts that vanish without a trace? Drop your answer below, and don't forget to subscribe. We've got more deep space mysteries coming your way. The cosmos is vast, unpredictable, and endlessly fascinating, and every click of that notification bell is another step into the unknown. See you out there among the stars.